We started the recording. So one of the things that we can do by applying force on an object is to move the object. We can turn another object, and the other thing that we can do is that we can deform the object. Now, deforming can happen in a lot of different ways. Basically, there are three different forms of deformation, which you don't have to know for your syllabus, but I'm just telling you. We can apply tension onto an object. Tension means something that will pull apart the object's different parts. So there will be pulling action onto the object, which will extend the dimension of the object on one linear dimension. The other type is that we can compress the object, which is actually squashing or squeezing the object into from two opposite sides, and we're gonna try to squeeze up or devolumize the object in from one linear axis. The third thing that we can do is that we can twist an object. Twisting essentially means that we're gonna set one side of the object stationary, and we're gonna apply some radial load onto the object. Radial load essentially means, uh, let me, if I put it this way, let's say if you consider the shape of a cylinder, let's say this is a cylindrical body, which is essentially a pretty symmetric object, and these are the two centers on the two circular sides. So let's say this is the axis of the cylinder. This is what we call the axis. If we apply some load onto the along the axis line, which means in this case horizontal forces, this is called axial load. If we apply some load that is perpendicular to the axis, that is called lateral load. And if we apply some twisting forces, that's called radial or turning load. Let me give you some examples. Let's say we have one of these things over here, and we somehow apply some clamps, and by human beings or by some machineries, if we apply two uh, forces away from each other, this is what we call tension. Vice versa, if we apply two forces which are gonna squeeze on the two faces, this is called compression, compressive load, which is gonna try to squeeze the object. Alternately, we can apply some load that will work perpendicular to the axis. For example, let's say if we apply some load like this is going to cause the object to become bend. Bend and twist are not the same thing. You have to understand this thing. I mean, whenever we apply some load onto a long object, if we apply some lateral load, something like this, as is shown in the figure, this object is going to try to bend, which means, let's say these two sides will pretty much stay in the same position, but we're going to have a bit of a curve at the middle going downwards. So that's what we call a bend or bend type of movement. So that is what we call lateral load. And the fourth type of load that we can do is that we can keep, let's say, one of the sides fixed to a solid structure. We can clamp this side up so that this thing would not move at all at any direction. And then we can, using some wrench or some pliers, we can do some rotational load onto the here. For example, let's say we clamp this up, and by applying some wrench, we try to twist it, something like a screw motion or a nut lever motion, something like that. So all of these things are something that we can do for deformation. I actually discussed a bit far beyond from the scope of your syllabus to give you an idea that what kind of deformations can we have possibly on an object. What you essentially need to learn from this for this chapter for your syllabus is actually pretty small. One of the primary thing that we're going to cover is what we call the Hooke's law. Now, important part about Hooke's law is that Mr. Hooke has in his name an E, so don't miss this out whenever you are writing this thing in your answers in any of the questions. Hooke's law has an E in his name. So the Hooke's law goes like this. Applied force is directly proportional to extension. This is the most common version that you have for your syllabus. In some cases, apart from the word extension, I sometimes information, because it is not exclusive for lengthening or process. It can be also it is also essentially proportional to compression cases as well. So if you are trying to squeeze up a screen by applying compressive force, then it will be also directly proportional to the deformation as well. So deformation is a more generalized term, but for your syllabus, the teachers, the syllabus makers, they mostly prefer this word, extension. One of the things that I would like to tell you is that elasticity is an inherent property of any object. Any object, I mean, that is applicable to both solid, liquid, and gas. Now, the elasticity property for liquid and gases is a bit more complex because it has to do with physical movement of the particles. So we're definitely not gonna do this in your O levels or A levels. We're gonna essentially work with the elasticity for solid objects. Now, solid objects do have the elastic behavior because of molecular arrangement. Because in solids, particles are stuck in their fixed positions. They don't want to move permanently away from their position. So by applying force, we can change their intermolecular spacing or intermolecular location. Now, there are basically two types of deformation that we can talk about. One that we call elastic deformation, or that is reversible deformation. You can remember these two words. I'm going to write them down just to help you remember. Uh, Elastic deformation, elastic or reversible deformation. আমার হ্যান্ডরাইটিং এমনিতেই খারাপ, তারপর আরো এই রাইটিং প্যাডের পিছলা সারফেসে লিখতে গিয়ে হ্যান্ডরাইটিং আরো খারাপ হইতেছে। সো ইফ ইউ নিড মি টু reread something for you, please
আগে তো
just
ভালো ছিল,
হ্যাঁ
আগে তো ভালো ছিল
কোনটা
হ্যান্ডরাইটিং।
টাইপ করেন উপরে যে টেক্সট অপশন
টাইপ করলে এখন আবার আমাকে বারবার মানে কার্সর মাউস আর কার্সরের মধ্যে সোয়াপ মানে কিবোর্ডের মধ্যে সোয়াপ ব্যাক করতে হয়। This feels more natural, but if you
না,
have
মাউস দিয়ে যে আগে লিখতেন ওইটা সুন্দর ছিল।
কোনটা
আগে যে লিখতেন আগের ক্লাসগুলোতে।
প্র্যাকটিস হয় নাই তো অনেকদিন ধরে।
What? It will come by. I hope it does come by. So, and then we can have plastic deformation or irreversible deformation. Let me irreversible, yes, deformation. These are two types of deformation that we can have. Let me talk about these stuffs a bit. Elastic deformation is something that if we apply some force on an object and we do some extension or compression, we do some deformation onto a solid object, and after applying a certain amount of force, if we start to remove out the force, if we start to get unload the object, we take away the deforming force, and when we have removed all of the forces, if the object completely comes back to its original dimensions, that's what we call an elastic deformation. So this is pretty easy for us to understand. For example, one of the things that I can tell you, which is actually a very simple example. Let's say if you have what? I could actually show you one of the videos. Should I pull that up? Oh, it's not important. Achha, never mind. So let's say you have a rod that is clamped on the side of the table. So this is a table. This is a clamp, and we have a rod clamped over here. And over here we have some hanging mechanism, and you can apply some loads over here. So you're gonna slowly add load, and as you're gonna further add load, this thing is gonna start to bend. Let's say it's gonna bend in this shape, and as it's gonna become more and more down because of the applied load. So more load, as you apply more load, it's gonna become more heavier, and it's gonna become more curved. Then if you start unloading the whole thing, and whenever you have taken all the deformation load over here, if the object comes back to the straight shape once again, that type of deformation is what we call the elastic deformation. But let's say if we apply such a high force that eventually the object does not come back to the original shape, it tries to, but it cannot come all the way back to its original dimension, that type of deformation is what we call the plastic deformation or irreversible deformation. So these are the two types of deformations that we can have. So one is permanent or plastic or irreversible, and the one is elastic, or you can say temporary, or you can say reversible deformation. Based upon these two types of deformation, we can have for an object force exertion graph. This is a very what I'm about to show you over here is a very simplified version of a force exertion graph. actually different materials can have a lot of different type of different type of representation for how their behavior works. So F is the applied force that is causing the deformation. X is the amount of extension or compression depending upon what type of load you are applying. So in this case, the F is actually the, what you can say, it's a lateral load. So for this example, I was applying a load perpendicular to the axis, because if this is a rod, the X should be horizontal. The adjoining line across the two centers of the circles on the two opposite sides of the rod, and then we can apply some load to make it bend. So this is a radial load, not radial, this is a lateral load. So if we plot a graph of force versus extension, the typical way metals behave, not essentially metals, the typical way most of the materials behave, I'm saying most because there are some other differences for polymeric substances, which we're going to cover a bit later, is that for a pretty significant part to begin with, they give us a pretty beautiful straight line. So let's say something like this. And this straight line represents that the further you are going to apply force, you're going to have a proportional increase of extension. So more force, more extension. And this line will definitely pass through the origin, which means that this is a y equals to mx line. Y equals to mx means y proportional to x. There is no y equals to mx plus c. So there is no intercept. So this represents a perfectly directly proportional relationship. This is basically the representation of Hooke's law, that applied force is directly proportional to extension or deformation, for example. So this part is dealing with elastic behavior, which means that if we apply the force, the extension is going to increase proportionally. If we then start to reduce the force, if we start to take the load off from the object, then it's going to have less deformation, and eventually when the applied load would be zero, so that means we have removed all the load from off the object, it would essentially come back to its original dimension. So extension will also become zero. This is the part which follows Hooke's law, and the gradient of this part is what we call the spring constant. If you wonder that if for a rod, where does the term spring constant come from? The spring constant is a term that we usually use for springs, but this is a more generalized term that can be used for many other cases as well. So the gradient of this linear part is what we call, so I'm going to write this over here, the gradient is called the spring constant. Sometimes this spring constant is represented by the term small k. So in many cases, if you see the mathematical representation of Hooke's law, you might also as well come like this. Let's say you're going to have f proportional to x. This is the general proportional relationship for the law. And then if you convert this into a mathematical rule, you are going to get f equals to kx, which where this k represents the Hooke's law. And if I now subject the k, I'm going to get k equals to f by x, which can be also written as multiple different values of x and k. So let's say f1 by x1 equals to f2 by x2 divided by x equals to f3 by x3. It can goes on for a lot of different values, all of which should belong onto this line. So it can work that way. For your syllabus, for your O-level syllabus, this end point of this straight line part is called the limit of proportionality. The graph is not finished over here, it goes further down the line. So I haven't shown you all the part. I'll show it to you a bit later, but I'm just covering up what is embedded within this part. The end point of the straight line part is called limit of proportionality. So that's another thing that we have to remember. If we apply more force onto this specimen, that is on this axis, let's say this is the maximum force up till which the limit of proportionality is. Let's say this force is some value, let's say it's 500 Newton, for example. So the limit of proportionality for this specimen is 500 Newton, which means up to 500 Newton of applied force, the object can behave reversibly, or it does undergo elastic deformation. This region is what we call elastic region, because here the deformation is reversible. You apply force, object undergoes deformation, you remove the force, object simply comes back to its original dimension. So no big deal. If we start to apply a force that is certainly bigger, somewhat bigger than the limit of proportionality force, then the object would start to represent some plastic behavior. Some plastic behavior. It will not be altogether plastic behavior. Let me just show you what I mean. So let's say if we apply more force, the typical way objects behave beyond the line of the limit of proportionality, it goes on like this. It takes a bit of a curve of decreasing gradient. It reaches up to a peak, and then it can start falling downwards. And beyond this, somewhere over this point, we can have a lot of different falling line over here for different specimens. But ultimately at the point, we can have a breaking. This cross sign at the end of these lines depends that the object is gonna shatter into pieces, or it is gonna become disconnected at one of its continuous line. Which is pretty simple, that if we apply long enough force, I mean, let's say if we apply seriously big enough force, it is definitely possible that this object can tear up from this clamping point, because it wouldn't be able to hold infinite amount of force. That's not going to happen. So that's the typical behavior. Another thing that I want you to understand, that I have not given any unit over here. So this figure is a sketch figure. This is not drawn to appropriate scale. Or there is no Newton or kilonewton or meganewton or giganewton, or there is no meter, centimeter or millimeter or micrometer given. So this is the approximate shape for how typical metals behave under the application of deformation force. One of the interesting things that is important, that this point is introduced to you as the Newton proportional, which is perfectly all right. Somewhat inside this point, inside this curve, there is another point that's called elastic limit. Now, elastic limit is not supposed to be known by you according to your syllabus, which I can assure you, and I'll show this to you so that you don't feel bothered by this. Many of you might. That's why I'm taking this effort.
Sir,
Yes.
can we get a prayer break?
Oh yeah, sure. Yeah, it's time.
ছয়টার দিকে দিবেন
না আমি জাস্ট এই জিনিসটা দেখাই তোমাদের প্রেয়ার ব্রেক দিচ্ছি, ডোন্ট ওয়ারি। You can resume at 5:05. Just a moment. Yeah, thank you. Thanks for reminding me. Dynamics master. Here's the deal. Recognize the significance of the term limit of proportionality for an elastic solid. An understanding of the elastic limit is not required. So you don't have to know what elastic limit is. So I'm not going to get into that discussion. I just wanted to show you that I don't have to discuss this, so that I don't fill your head with more unnecessary information. Okay, we'll take a break for prayer. We'll resume the class at 6:05.
স্যার অডিও অফ
Okay, so yeah, thank you. We're back. I resume the recording. So this endpoint, the endpoint of the straight line, is what we call the limit of proportionality. And because of this limit of proportionality, we can divide this entire graph into two specific regions. I'm going to use some oval shapes over here to label those parts. This is the part, oops. This segment of the graph is what we call the elastic region. This is this segment of the graph up to the elastic limit of proportionality, all the way up to here. And the other part is what we call the plastic region. So let's say this is the part that we call the plastic region of the graph. So they have two different names. I'm gonna write those names. This is
স্যার প্লাস্টিকটা আবার একটু বলবেন প্লাস্টিক রিজিয়নটা
the part that is not linear, that the part that is starting from after the elastic limit of proportionality, where the object undergoes permanent deformation. So that's pretty much it that you have for your syllabus. You have some simple maths to work with, and those maths are usually pretty simple because we only have to deal with one simple formula that goes by F equals to kx. So that's pretty much it. There are a couple of things that I'd like to help you to understand. What I need you to understand, that this is the extension. extension of an object, to make sense of the extension, if let me just change this apparatus setup by a little bit. Let's say we have a ceiling over here. We hang some spring from the ceiling to give you a bit of an idea, and we have a mechanism to apply some load over here. So let's say currently this is the natural length of the object. So let's assume that from the starting part of the coil all the way to the end part of the coil, this is what we are labeling as, let's say, L. So L is our original length of the spring. If we, whenever we'll apply some load, this spring is gonna extend out. So I'm gonna try to draw a bit longer spring over here. So let's say this is a bit of a longer spring, and we have the setup essentially with some loads in this place. So we have placed some loads. So now we have the extended length of this much part. Let's say this dimension is labeled as L prime. We can have a lot of different annotations for this length representation. Sometimes this is called as L naught, which means the L of initial. It is, and this one is labeled as L. But irrespective of the names, you have to understand that deformation is always the difference between the extended length minus the original length. That's basically the key idea. So if we ever plot a graph of force versus extension, something like this, we will always have the graph starting from the 0 point. What if we plot a graph that goes with the axis, which happens to be plotted from F versus L? Let's say in this case, L is the length of the object at any point of time. Now, have to have a look at the difference. This was this graph was F versus X, force versus extension. This graph is force versus length. The interesting part is that if we are trying to plot force versus length, whenever we have not applied any force whatsoever, it would still have some length, which means the length of the object can never be zero. At zero applied force onto the spring, the length was this much. So let's say the graph would start from this x-axis intercept, where this value is essentially capital L, the original length of the spring. Then as we're going to start apply load onto this hanger, so if we apply bigger and bigger force, then the graph is going to start from this point, and it's going to have the exact same characteristics as we have discussed earlier. So we're going to have a little bit of straight line part. So let's assume this is a straight line part. My hand drawing, so it's not very straight, but bear with me. So this is the limit of proportionality. I'm going to limit of proportionality. So in this case, this graph is not going to the origin, because this was not plotted for force versus extension. This was plotted for force versus length. So we have a bit of a dead space or intercept on the x-axis, because this part represents the original length. And from this part starts the change of length, or what you call that extension. So this is important, that whenever you are trying to answer questions, especially for the MCQ parts, that you be very careful to observe that what is the length axis represented as. Is it the extension, or is it the actual length of the spring? So these are the two variables that you really need to take care, so that you don't feel confused or miss out on the marks. We can try to look out for some of the MCQ questions, which can give you some idea for how easy they are. Something like this. Let me zoom in on. You have this entire booklet to you, so you can turn up your book and have a look at there, or you can keep observing the lecture, which anyhow you feel comfortable with it. Question number 1 says that a student wishes to plot an extension load graph for a spring. He assembles some equipment. Which of the following is not needed? Which one do you think is not needed?
Watch.
Essentially stopwatch. Yes.
Stopwatch.
Labiba, you have some question?
Sir, I wanted to say that time that wouldn't the force be on the x-axis and the length on the y-axis?
We can well, typically whenever we plot force extension graph, whenever we define that, whenever we name a certain graph, usually always the first variable is what we plot on the y-axis and the second variable is what we plot on the x-axis. But any graph can have an inverted version as well. I mean, if you can plot a force extension graph, logically you can also plot a graph of extension force graph as well. For example, in question number 4, just to be having a little bit of a jump, or for question number 3 as well, you can see that this thing is named as extension load graph, so which means the first variable goes on the y-axis, second variable goes on the x-axis. So extension is plotted on the y-axis and the load is plotted on the x-axis. So other than having a decreasing gradient like the way I have discussed over here, so beyond the limit of proportion is supposed to lose gradient if it is force extension graph. If you just reverse the two axes, the entire graph is also gonna become 45-degree reversed. So that way you're gonna have increasing gradient. So that's essentially what was shown in this part as well. So it's going up in the increasing pattern. This is also very much possible to plot depending upon what you want to achieve, and questions can also be set in this way. There is no hard and fast rule that it has to be that force has to be plotted on the y-axis and extension or length has to be plotted on the x-axis. They can be vice versa at any given time. Bucho?
Yes, sir.
Okay. So let's look at question number 2. The table shows how the extension of a spring varies with load. Between which two loads would you find the limit of proportionality? So they're trying to, so if you have a look at the table over here, we have the load list. You can see that we are increasing the load with 2 Newton increments. So we have 0, 0, and then we are increasing it. And the question is asking us that between which 2 points should we have the limit of proportionality? Now, interesting point.
0 to 2.
10 to 12.
No. Let me explain. For many of you do understand this thing, that up to the point of limited proportionality, the force and the extension should be proportional to each other. So let's try to have a look. 0, 0 is the starting point, so there is nothing to have a proportion over here. But if you have a look for the first two non-zero values, for 2 Newton force, you have an extension of 3 centimeters. So your ratio is 2:3. This one still 2:3.
2:3.
One still 2:3.
2:3.
This one
4:2.
no.
2 is to
Still 2:3.
4:6.
2 is to 3.
Which is 2:3. This one, if
Two
you
is to
divide by
three.
5, you still get 2:3. But over here, you have a change of that ratio.
3 is to 5.
This ratio is 3:5. If you reduce it to the smallest component, this is 3:4, 3:5, which means up till this point, we have a fixed ratio between load and extension, which means up till this 10 Newton value, we essentially had a proportional relationship between the load and the extension. But after the 10 Newton applied force, the load and extension, they are not proportional anymore because the ratio got changed. So this goes on to prove that the limit of proportionality must exist between these two values. So it definitely is above 10 Newton. It definitely is below 12 Newton, because somewhere in between, because we are increasing the force over here with 2 Newton increments, which essentially means that we cannot exactly pinpoint where that force is unless we plot a graph. But exclusively by just looking at the values available on the table, we can essentially ascertain that the two values in between which the limit of proportion might exist would be between 8 and 10. No, sorry, 10 and 12, right? 10 and 12 Newton. So which one is the correct response? 0, 2. C is the correct response, I believe, right?
Yes, sir.
Yes,
C.
sir.
C is the correct response, yeah. Beautiful. Number 3, which one do you think is the correct response for number 3?
B.
B.
Essentially B. Beautiful.
B.
Number 4.
D.
Give it a try. Read out the question before I help you.
Sir, B.
3 centimeter.
So 3 centimeter is to 5 Newton, which is B.
No.
D, right?
Yes.
Oh, sorry, got it.
have a look. What is the column heading for the y-axis? It's the length of the spring. Take a good look. It's the length of the spring, not the extension. The question says a spring balance is calibrated to give readings in newtons. The graph shows how the length of the spring varies with load. A load causes the spring of the balance to extend by 3 centimeter. So you have an extension of 3 centimeter. But you can see from this graph very well that this is the unstretched length, that is 2 centimeter. If we have an extension of 3 centimeter, the total length should be how much? 5 centimeter?
5
And
and 15.
the respective load for 5 centimeter is 15 Newton exactly. That's why D is the correct response, not B. Hold on, দেখো বুঝা যাচ্ছে কিনা? This is the key observation that I was talking about, that you have to be careful. If the axis is not extension, it is length, then you have to be careful and use your mathematical brain to get the answer. So correct response for this one is 15 Newton. D is the correct response. 5 is a repeat question, so I'm not gonna bother by it. 6, question number 6, let's have a look for it. Give it a try. The most important word for this question
C.
is the word further. Be careful about that. It says further 3 Newton.
Yes, sir. C.
Correct response is C, but see if everyone can get this. It's actually pretty simple. I'll be helpful for it. It says it extends by 4 millimeter when a load of 2 Newton is added to it. What will be the length of the wire if a further 3 Newton is added to it? So if a further 3 Newton is added to it, total amount of load it would be experiencing is 5 Newton. So what we're trying to find out is that how much extension should it have under the effect of 5 Newton. So you simply can apply the unitary method because in this case it will work, or you can go for F equals to Kx, that also works. So I'm gonna show by F equals to Kx because that's a formula that you might as well practice to learn. So what we have is F1 by X1 should be equals to F2 by X2. If you wonder where does this come from, this is because F proportional to X essentially means that F equals to Kx. So K is the constant, so K is equals to all the ratios of F and X. So you can have this ratio at a very large value. According to the question, whenever you are applying 2 Newton, you're having an extension of 4 millimeter, I believe. Was that the value? Yes, 4 millimeter. So you're having an extension of 4 millimeter. So if we apply a force of 5 Newton, what should be the extension? So you calculate out the value of x2 from this equation, and that should give you 10 millimeter. 10 millimeter in converted into meter would be 0.010 meter. So the total length of the wire should be 1.010 meter. And that's the final answer. ক্যালকুলেশনটা দেখো, না বুঝলে আমাকে জিজ্ঞেস করো, anyone.
স্যার আর একটু বুঝাবেন।
হ্যাঁ বলতেছি, we are trying to find out what will be the extension of the spring under the effect of a 5 Newton force. Where does the 5 Newton come from? Because the question says that further 3 Newton is added. So 2 Newton was already added. If we have added further 5 Newton, we will have a total of, if we add a further 3 Newton, we're going to have a total of 5 Newton force. So we are trying to find out that how much extension should this spring have under the, this wire have under the effect of 5 Newton force. So this is the formula that we're using, F1 by X1 equals to F2 by X2. This part is known to us, that under an effect of 2 Newton force, it had an extension of 4 millimeter. Using the formula, we are now replacing the new force, which is the unknown, 5 Newton force, and we're trying to find out what is the new extension should be. So that's the basic replacement of the formula. We find out the new extension value. This is not the original full length. This is the exclusively the extension. To get the full length, you have to add this much with the original length, which is 1 meter. So we add this thing to the 1 meter, and we get the total length of the metal wire. বুঝছো?
Yes, sir.
আচ্ছা, আসিফ একটা কোশ্চেন করছে আমাকে প্রাইভেট। আসিফ, you can also write the questions in public chat as well, no big deal. What if the question said assuming it extends beyond the proportionality limit? Well, there is a thing. If the extension happens beyond the proportionality limit, there is no way we can apply this formula, because this formula is exclusively applicable within the linear part of the graph, because this is a directly proportional relationship. So this is y equals to mx. If we are asked to find out any value of extension or length beyond the limit of proportionality, we must have access to a properly plotted graph on a grid for that answer. We have to have that graph. Only from reading from the graph you can get that number. Other than that, there is no mathematical way to get that value that is introduced at your level. You cannot do that. So without the graph, এই কোশ্চেনটা কোনো সময় বলবে না। আসিফ, বুঝছো? আচ্ছা, so acha, let's look at the next one. Number 7, which one do you think is the
So
correct
D.
response?
D.
D.
D is the correct response. 8.
A.
The graph shows how the extension of a piece of copper wire as the load on it is increases. What does the graph show? At a certain load, the wire becomes easier to extend. A certain load, the wire becomes harder to extend. The load and extension are directly proportional for any load. The inverse proportional for any load. Okay.
So A, I think too.
C and D are actually essentially out of the question. Now let me elaborate. Yeah, A is the correct response for this question. Let me elaborate what it actually means, easier or harder to deform. What does that term essentially mean? I'd like to elaborate this a little bit. What I want you to understand, if we plot the graph of multiple objects for force exertion scenarios, let's say if we plot on the same graph the force exertion for 2 different metal wire. Let's say one metal wire has a force exertion graph that look like this. I'm just drawing the linear part. I'm not going for the other part. And another wire on the same scale gives us a force exertion graph for the linear part that looks, let's say, something like this. Between these two wires, which one is easier to deform? Now, what does that term mean essentially, easier to deform? Easier to deform means that to achieve equal amount of deformation, you'd have to apply less force. Or in other terms, if we apply equal force to both of them, one will extend more, the other one will extend less. The one that will extend more is easier to deform. So between these two wires, brown and red, which one do you think is easier to deform?
Red.
Essentially, the red is easier to deform, because if you want to achieve the same amount of deformation, let's say if I assume to draw a small thin line for a random extension, let's say if I want to achieve this much extension, for the red we'd have to apply a pretty small amount of force, only this much. But for the brown, we have to apply a very large amount of force, which means between these two wires, the one that has a lower gradient on the force extension graph is easier to deform. So that's the idea. Whenever this graph starts to lose gradient, so which means steeper graph means harder to deform, and slanted graph means easier to deform. If I now consider the actual graph for a single piece of wire, what we have seen that for a starting behavior, we have a linear behavior, and then the graph slowly loses gradient. Whenever the graph loses gradient, it essentially means that it becomes easier to deform, because then to achieve the same amount of deformation, you would have to you would not require to increase the force by the same proportion. You can reduce the force by increase the force by a smaller amount. Let me tell you, elaborate mathematically what I mean. Let's say if this is the limit of proportionality, let's assume this is the limit of proportionality. Up to the limit of proportionality, the amount of extension is this much. So if you want to extend the object from its natural state to this point of extension, you have to apply this much force. Okay, works. But if you want to achieve beyond the limit of proportionality the exactly same amount of deformation, let's say if I want to double this line, would you have to apply the double amount of force? Let's try this out. If I just go above onto the graph and extrapolate this point onto the force axis, you will find out that the required force is simply not double. To achieve this much extension, you have to apply this much force. To achieve additional equal amount of extension, you only have to apply this much force. So you did not have to apply same amount of force, rather you have to apply a less amount of force, which means deforming the object actually became easier. বুঝা গেছে কি বলছি?
জি
Yes,
স্যার।
sir.
Okay, so this is why A is the correct response for this question. Beautiful. Number 9.
C.
C.
Yeah, that's obvious. The
সি
end point of the linear part. Beautiful. Okay, that's also pretty. Shows the limit of proportionality for this solid limit of proportionality. Okay, I would like to ask you, tell you one more thing. The length of this graph represents the elastic region. For example, O is the origin, OP is the elastic region, P is the limit of proportionality. Limit of proportionality is the name of a point. It is not the name of a length of variation. And then PQ is the plastic region, or you can say permanent deformation region, so plastic region. So limited proportionality is a point of the graph. So that's why the correct response for this is P, not OP. Sometimes students mess up and give OP. OP is called the elastic region, and PQ is called the plastic region. P is the distinguishing point between them, which is the limit of proportionality, borderline. Question number 11 happens to be the most interesting MCQ of this entire paper. I'd give you some time.
স্যার ইউনিট কি চেঞ্জ করতে হয়?
I'd give you some time.
না ইউনিট কি চেঞ্জ করতে হয় এখানে লেস্টিকে?
I'd give you some time. ট্রাই করো, তুমি যেভাবেই পারো। ইউনিট ওয়েল সবগুলো যেহেতু সেন্টিমিটারে দেওয়া আছে, ইউনিট তোমার চেঞ্জ করা লাগবে না, কারণ আলটিমেট আনসারও তুমি সেন্টিমিটারেই প্রডিউস করবা। সো ইউনিট চেঞ্জ করা লাগবে না। যদি এখানে সেন্টিমিটার এখানে মিটার বা মিটার সেন্টিমিটার যদি মিক্স আপ করা থাকতো তাহলে অবশ্যই চেঞ্জ করতে হতো, বাট যেহেতু সবগুলো সেন্টিমিটার আছে, ইউ ডোন্ট হ্যাভ টু বদার। Try number 11. I'll help.
So C 39.7.
I think C might be the correct response. I'll have to check. আনসার কিতে চেক করা তো হয়েছে কিনা, কারেক্ট রেসপন্সটা কি, আমার আনসার কি প্রিন্ট করা আছে কোনো এক জায়গায় বাই করতে হবে, নাহলে এখানে আবার পিসি থেকে বের করতে হবে। আনসার কি একটু দেখো তো, আনসার কি দেওয়া?
I think C.
সি দেওয়া?
Let's see.
আচ্ছা,
Let's see. I haven't checked yet. Let me check. Yes, sir. C.
okay. Sit tight and let other have some time.
স্যার এখানে বুকলেটের অ্যান্সার বি।
Well, we cannot have two different booklets.
Sir, can you show the question again?
Yeah, just a second. 11. No, 11 answer C though. Yeah. Yes, it's Hooke's law. C. Yep. What seems to be the primary problem of this question? The original length of the spring is not given, right?
जी sir.
If the original spring of the length was already provided, had it been already provided, then this would have been much too easier, but it is not provided. So a few things that we can essentially take care is that we can try to build up the information that we have over here. So I'm going to take up this quotient and bring it up over here. Let's see if we can do something. Okay, that's about enough space. So it says 100 gram mass is suspended from the spring next to a vertical meter rule. The top of the spring is level with that 0 centimeter mark. The bottom of the spring is level with 27.2 centimeter mark. The 100 gram mass is replaced with a 600 gram mass. The length of the spring is now 89.7. The spring has not reached the limit of proportionality. The 600 gram mass is now replaced with 200 gram mass. What is the length of the spring? So let's try to do stuff. For example, let's assume that for 100 gram mass, right over here, let's assume that extension is supposed to be x. So this entire length, 27.2 centimeter, has the original length of the spring plus the extension for 100 gram mass as well. So I'm going to write this up over here. This is just one way to solve the problem. There are multiple different ways. I'm just showing you one of the ways that is easier to understand, but it's a bit elaborate, but it's easier to understand. So let's assume that for 100 gram mass of load, we have an extension of x. So I can write, following the formula F equals to kx, I can write that 100 gram, so let's say 100 into g, this is the gravitational acceleration, g, mg, equals to K into L plus X. See if it makes sense. Did I just write it wrong? I might. No,
But if K is supposed to be there.
I don't actually have to have this equation. Sorry. This is all right. I could write this, but I don't need this. What I can write, actually, I was thinking the other way around.
I use the f by x equals to f1 by x1 thing. So
this is the first equation that I am writing, that L plus X equals 27.2. Next thing it says, the 100 gram mass is now replaced with the 600 gram mass. Now try to think about it. If you have for 100 gram mass, if we assume the extension to be X, what would be the extension for 600 gram? 6x. Take this out. এটা কি ঠিক আছে? এই লজিকটাকে বুঝতেছো?
জি স্যার।
So I can write over here L plus 6x is supposed to be what? 89.7. এই দুটো ইকুয়েশনকে সাইমালটেনিয়াসলি সলভ করলে আমরা L ও পাবো X ও পাবো। পাবো না? এই দুটো একটু সলভ করো। সলভ করে দেখো কত কত আছে।
সাইমালটেনিয়াস।
Yeah, you can just subtract to get the value of X and then you, solve this to find out the value of L and X.
So I didn't understand the second equation.
Oh, the second equation says that the 100 gram mass is replaced with a 600 gram mass. So whenever we're going to replace this thing with a 600 gram mass, the spring is going to be farther long. And then the bottom of the spring or the length of the spring will become this much. So this much is the total length of the spring under the effect of a 600 gram mass. Within that length, we have the original length and also the extension due to the load. So how much is that extension supposed to be? That extension is happening under the effect of a 600 gram mass. Because we know that what? F equals to Kx, so force is directly proportional to extension. I assume that for a 100 gram mass, the extension was X. So logically, 600 gram of mass should give you 6x deformation. Because they are proportional to each other, force and deformation are proportional to each other. So if you we increase the force by 6-fold, so the extension should also be 6-fold. So this new total length should be the sum of the original length plus 6 times the deformation for what deformation we had for the 100 gram mass. That's the second equation.
So doing this gives 5x equals to 62.5, which means x equals to 12.5. Now we add that 12.5 to 27.2 and get C 39.7.
Yep. So x equals to 12.5 centimeter. So what does that make the L? L would be, I think, if we do the subtraction. এটা সাবট্রাক্ট করলে কত হয় বলো?
89.7 minus 27.2.
এটা কত? আমার কাছে ক্যালকুলেটর নাই এখানে দাও।
So 62.5.
না, L এর ভ্যালু আরো ছোট হবে। L কত হয়?
Oh, let me check. So let me check.
27.2 minus 12.5. 14.9. No, 14.7.
14.7.
40.7 na?
Yes, sir.
Yes, sir.
14.7.
40.7 centimeter. So once you have these two values, finding out the next part of the question is pretty simple, because it says that now the 600 gram mass is replaced with the 200 gram mass. So what is the length of the spring? So what we are trying to find out is L plus 2x equals to what? If you have the value of L and X, you can very easily find this out. What Amin Hamza just proposed, that other than finding out the value of the L, we don't have to find this out. Actually, we don't. Once you find out the value of X, you can very easily add the X with this one, because we already had the value of L plus X. We want to find out what is L plus 2x. So essentially, what do we have to do? We have to add with L plus X another X. ঠিক না? Think about it. আমাদের অলরেডি L plus X এর ভ্যালু অলরেডি আমাদের জানা আছে, সেটা কত? 27.2. সো আমরা যদি X এর ভ্যালুটা অলরেডি বের করে ফেলি, আমরা তার সাথে আরেকটা x অ্যাড করে দিলাম 12.5 যদি এটার সাথে অ্যাড করে দিলে আমাদের l plus 2x বের হয়ে যাবে that should essentially be your answer so ওটা তুমি করতে পারো you can skip the finding out the value of l if you don't want to if you can take that jump or you can directly do it in the exact mathematical way solve make up these two equation solve this equation then find out l plus 2x in a very traditional way which also perfectly works whatever you can capture easily you can remember it more easily whatever that makes your brain accept far to more retaining way that's what you adopt perfectly all right বুঝা গেছে কি এই কোশ্চেনটা কেন ইউনিক because you cannot directly use f equals to kx you have to work around with mathematical equation building and simultaneously solve these two equations that's the only way you can do this thing any question so far তোমার ফার্দার একটু দেখো পুরো সলিউশনটা দেখো কোনো কোশ্চেন থাকলে আমাকে করো and then we'll move out from this question any question anyone nope so let's move on okay this is also a repeat question okay one of the things is 12 question number 12 question number 12 is about the combination of springs combination of springs আমি তোমাদেরকে পড়াই নাই এটা একটু পড়াবো then we can essentially go into this part combination of springs is actually pretty simple so let me directly tell you this combination of spring first thing first combination can be of primarily two types one is what we call a series combination series combination means one after another so they're all joined up along a single straight line the second thing is what you can have is a parallel combination parallel combination means side by side side by side so this is the two type of combination that you can have series combination and parallel combination what is going to happen let me tell you if we have let's for example let's assume that we have a spring we have a lot of springs which are all identical the behavior of the spring is that if we apply a load of w onto this one it undergoes an extension of x so this is one of the ways that we can show that what this figure essentially means without the application of the w load the spring was this much long let me choose a different color without the application of the force the spring was this much long after applying the force the spring has become this much long so which means this is the extension so under the effect of w load we have an extension of x so let's say we have this spring in a lot of number we have identical springs which are in a lot of number there are two different ways we can pair them up one of the ways we can go for okay one of the ways we can go for is by series series combination is going to look something like this if we have one spring and at the bottom of another spring let's say we add another one so I am let's say as adding two of the springs in series now if I apply the same w load over here how much long would this whole combination become? Would it still extend by x, or will it extend by more than x or less than x? What do you think?
More.
There was one response. One of the person said more. There are 19 left in the group.
Can you repeat the question?
If we add two of the springs in series, one after another, and apply the same amount of load W as it was done in this case, what would be the total extension of this whole combination? Total extension of the whole combination. Would it be more than x, equal to x, or less than x?
More
Equal
than
to
x.
x.
Equal to x.
Equal.
Equal to.
Equal to
Okay. Let me help you to understand.
Equal to x.
Okay, yeah, I really appreciate the responses, but let me explain. This thing is perfectly stable, right? This thing is perfectly stable. If we apply W load over here, this load would work on all the sections of the object. Let me elaborate what I mean. Think about it. If you have a piece of string, let's say you have a piece of string. If you apply a 1 kg load over here, you would have a 1 kg weight of tension on every single point of the string, right? The entire rope would be taut. ঠিক না? It's not going to be that in some places the rope has half kg weight of or the force. In other places it has more than 1 kg. The entire string would have the same 1 kg. I mean, 1 kg means what? 10 Newton. 10 Newton of force along its entire length. Is that correct?
Yes, sir.
Everywhere the force would be same. So this is what I'm trying to mean over here. This support point is perfectly rigid. So whenever you are applying W load over here, this spring would essentially experience the W load all together. So as a result, this spring will undergo an extension of x. So what's going to happen? This is going to come down by a level of x. So if this was your original level, and this is the new level of the top spring, this much would be x. Now comes the second point. Earlier, the starting point of the second spring was here. Now it has already come down by a value of x. So the second spring will now start from here. And because the W load would still apply on this load as well, because this W load is working along this line and on the entirety of the structure, So this load will also extend the second spring by another X amount. So this will also have, if this was the original length of the whole spring, second spring, this second spring will also extend by X. They'll both extend by X, and as a result, the total amount of extension under this thing would be 2X, because each individual spring would be subjected to the W load. It will not be lessened by each other. On the other hand, let me show you the parallel one, then I'll take questions. Don't worry, I'll answer your questions, confusions as well. On the other hand, if we have a parallel combination, let me show you this with, let's say, red. Let's say we have a situation like this. We have two, this is a solid support system, ceiling maybe. We have two of the springs placed side by side, and we have a support system over here. Let's assume the weight of the support system is 0, and we apply the W load over here. This W load, because this is now being added on two springs side by side, would be shared between these two springs. So this will share half the load, this will share half the load, because together they have to support W load. So this will be pulled down by an individual W by 2. This will be pulled down by an individual W by 2. So this will have an extension of X by 2, which I should show in a different figure. Shouldn't draw this on the same figure. So in this case, this will come down under the effect of W by 2 force, because W was proportional to X. W load gave us X extension. So if we have half the load, it will extend by also half. So it will come down by X by 2. And the second spring will also come down by X by 2. So this was the original level of the two springs bottom. Now the new lower level should be X by 2 below the original level, under the effect of W load. So in altogether sense, how much did the total extension of the whole combination is that? What is the total extension of the whole combination? Is it X by 2 plus X by 2 X, or is it only X by 2? how much longer did the combination get?
Only x/2.
Asif, তোমার question answer to পড়ে দিচ্ছি. Here the two extensions happen side by side, so the total extension of the combination would be only x by 2. You don't have to add them up because they did not happen along the same line, which happened over here. Another easier similarity that I can give you is like this. Let's say we have a drum on over here on the ground, rolling on its side. Not so this is the ground. Let's say a person comes in, pushes it by 1 meter, and then another person comes in and pushes it by another 1 meter. The total movement of this drum would be 2 meter. That's one way. In a different case, let's say we have another drum over here, and two persons comes in on two sides, and they both push the drum by 1 meter. What will be the total movement of this drum? Should it be 2 meter or should it be 1 meter?
1 meter.
It would still be 1 meter. They're both pushing, so they are individually pushing by less force, exactly half the force for what happened over here. But they are both pushing the drum by altogether 1 meter. So this is what is happening for the parallel case. This is basically what is happening for the series case. So whenever the springs are connected in series combination, the load would be applied for all the individual layers. For example, I mean by the word layer, I mean this is one layer, this is another layer, and the extension will happen for both of them. And whenever you have them in parallel, the load will get shared between the parallel combination parts, and as a result, the total extension will become less. So this is just a basic way to show how this worked. If we had more springs over here, it could simply become more. For example, if we had 3 springs in series, the total extension would become 3x. If we had 3 springs in parallel, the total extension would become x by 3, because then the load would be divided in three ways, 3 equal ways. That's how the combination works. Now I'll take questions. Anyone? Asif Imran asked me a question. Will the mass of the springs affect the extension anyhow? In reality, yes. But for the sake of simplicity for your syllabus, we would not consider that it would have any measurable effect. In reality, yes means that if you have a pretty long spring and if you hold it from a pretty tall structure, you'd always see that the top part of the coils are more separated compared to the bottom part of the coils. What I mean is that if you have a pretty, let's say slinky, if you have a slinky, a very long spring would appear to be like this, like big gaps on the top and then slowly smaller gaps at the bottom because of the own weight of the spring itself. This is supposed to happen. This actually happens in reality. But for the sake of simplicity, a complexity ta tomader O levels e introduce kora hoy na, so you don't have to bother about that. বুঝছো? Questions, kids. এটা নিয়ে কোনো কোশ্চেন কিনা দেখো, এটা অ্যাপ্লিকেশন আমরা দেখবো, দুটো এমসিকিউ আছে এটার উপর, সো we'll see about them as well. Let's have a look for number 12. Which one do you think is the correct response?
So B. It's B. Because each of them are handling 15, and so 10 to 15 is 2 to 3, so 2 to 3, 4 to 6.
Makes sense. So here, the two springs are connected in parallel, side by side. So the total applied load would be shared among them. So what would be the force experienced by one of the springs? Half of the total load, which would be 15 Newton. So all that you now have to do is to find out what would be the extension of one of the springs under the effect of 15 Newton. So you can go by F1 by X1 equals to F2 by X2, or you can do unitary method, or you can do it by ratio if you feel like, perfectly all right. So 10 Newton applied force, in this case, 10 Newton applied force gives us an extension of 4 centimeter. So how much extension should we have under the effect of 15 Newton of force? That's what you're trying to find out. What do you think? There are actually many different ways we can approach these questions. Let me show you another way for this one. Yep. Yep. One of the ways that you can do it, the question says that a spring extends by force centimeter when a 10 Newton is suspended from it. So we could pretty well draw this scenario maybe in something in this format, let's say. So if we have one spring which is undergoing 10 Newton, it undergoes an extension of 4 centimeter. So let's first make this structure. So if we have two of the springs in parallel, and if they were still added by 10 Newton of force, then what should be the extension? Half of that? বলবান দেখো না বুঝলে রেসপন্ড করো. If we had two of them in parallel, the total extension should be what? 2 centimeter. Now, if this 10 Newton becomes 30 Newton, which means it becomes multiplied by 3, then this extension should also become multiplied by 3, because we all know that F is proportional to X. So if you increase the force by some fold, your extension will essentially become multiplied by the same factor. So 3 2s are 6, you can also get 6. This is another way to go by the structure of the combination, that you first draw the individual spring and then you make it into the structure that you want to get at, and then you can find out the number. Whatever makes you understand better. না বুঝলে জিজ্ঞেস করো, I'll help you.
Sir, could you explain this again?
Sure. First, I'm trying to draw the scenario that is explained in this sentence. A spring extends by 4 centimeter when 10 Newton is suspended from it. So that's what I am drawing over here. One spring experiencing 10 Newton force having an extension of 4 centimeter. So I do this part. That's the conversion of this sentence into the figure. Two of the springs are used as shown to carry a 30 Newton load. So now if we have two of the springs side by side as it is shown over here, so if we draw this up and apply the same 10 Newton force for the timing, then the extension will become half, because like the way I said that, because this 10 Newton will be shared between these two springs, so the 4 centimeter will become 2 centimeter. এটুকু বুঝছো কিনা দেখো.
Yes, sir.
আচ্ছা. But in the question, the total applied force was 30 Newton, not 10 Newton. So to make 10 Newton into 30 Newton, we have to multiply it by 3. If we increase the force by 3-fold, the extension should also become 3-fold, because force is directly proportional to extension. So if you increase the force by a factor of 3, your total extension of the spring combination also becomes multiplied by 3. So 3 2s are 6 centimeter. B is the correct response.
Okay, sir, I understood.
Beautiful. Anyone else? Question? নাকি বুঝা গেছে? Okay, I hope it's clear. এটা একটা repeat question, so I'll skip this. How about we try number 15? Why is this a question? Which one do you think is the correct response for number 15?
It's B.
A.
Why
Please
B?
A.
A. Should be A.
It should be A. Have
So,
a look.
but
In this case, you have one spring undergoing one load increased by 1 Newton. You have 1 centimeter. You now have two springs in parallel, so the load would be shared. So here 1 Newton increase happened on one spring. Here 1 Newton increase happening on two springs. So essentially, the amount of extension would become half because the load is being shared by two springs. So here we had 1 centimeter extension for the single spring. For a parallel combination of two springs, we should have half centimeter increase. A is the correct response.
okay.
Okay. 16. 16 is a pretty interesting problem. You don't have a standard case. You have to convert from a complex case into another complex case. So you are given a parallel combination. From the parallel combination, you have to move into a series combination. Just to help you, let me do something. It would be easier for you to attempt to solve this problem if you try something like this. Try to convert with the same value of load, keep the load same. Try to go from this. I mean, you have to understand, according to the question, here the extension of this setup is X. ঠিক আছে? The question is, what is the total extension of this setup? Try to go from here into one spring, 1L. Try to go from here to here. And then from here to there. This will be easier for you to achieve. Give it a try.
Sir, is it B?
Did you say D or B?
B.
Yeah, D is the correct response.
So could you explain how?
Sure. Try to understand. এই ফিগারটা যে এখানে যে x লেবেল করলাম, এই পার্টটা আগে বুঝছো কিনা দেখো। A load L is suspended from two springs that are in parallel. The extension of each spring is X, which means this one extends by X, this one extends by X, which means the total combination also extends by X. Now have a look. Whenever we had two springs, the load was being shared. Each of the total combination had an extension of X. If I now apply the same load on a single spring, the load would not be shared, which means the extension has to become double. Right?
Yes, sir.
Think about it. Here the L load was being shared among two springs. The extension was X. Here it is not being shared. So the total load would be applying on a single spring. So the extension should simply become double, which gives us this value should be 2X. From here to here.
Yes.
Yes,
If
sir.
you understand this much, then this part is pretty simple. If you apply L load, this extends by 2X. This also extends by 2X. Total extension should be how much?
4.
4X.
Thank you, sir.
Sure, no problem. বলুন দেখো বুঝা যাচ্ছে কিনা
Sir,
প্রসিডিউরটা
at the parallel one, shouldn't the extension be totally 2x?
আরেকবার বলো সরি বুঝি নাই আমি
At the parallel extension, why is it only x? It should be 2x, since we are taking the total extension. It should be x plus x, which is 2x, right?
No, that is the important bit, that extension of each spring is X. Whenever we have a parallel combination, try to understand, before the load was given, let's say before the load was given, the setup was at this level. This horizontal bar was at this level. After the L was applied, after the load was introduced, each of the spring extended by x. So this one had an extension of x, this one had an extension of x. So the total level came down by how much? Did it came down by 2x amount or did it came down by x amount?
X amount.
Think about it.
Got it. Yes, X amount. Got it.
বুঝছো?
Yes, got it.
তো প্যারালাল যখন হবে তখন তো সাইড বাই সাইড এক্স ডিফর্মেশন হচ্ছে। সো সাইড বাই সাইড ডিফর্মেশনের জন্য আমাদের ইন্ডিভিজুয়াল স্প্রিং এক্সটেনশনটাই হচ্ছে টোটাল কম্বিনেশনের এক্সটেনশন। I hope this is all right. So we'll move on to the next question. এখানে একটা কোশ্চেন আছে, এটা ট্রাই করে দেখো কত আসে। It's a pretty simple one, but still
It's a B.
solve it.
B.
Why is this a question? I mean, this is weird. আচ্ছা, 200 gram message original length is 7, 8. Oh, there is some reverse calculation that you have to do. This is a nice question actually. I was not reading it properly.
I think it's still B because when it was 200 grams, the extension was 2. So we
Yes.
know when it's 0, it's 7. So when it's 100, it's plus 1, so 8, so B.
Yes. বলুন দেখো, যে ইনফরমেশনটা দেওয়া আছে, spring has a length of 9 cm when loaded with 200 gram mass. This is the extended length, not the original length or not the natural length. So the extended length is 9 cm under the effect of 200 gram mass. You can see over here in the extension mass graph, for 200 gram mass, the extension is 2 cm. So within this 9 cm, 2 cm was extension and the remaining was original length. So the original length of the spring has to be how much? 7
7.
cm?
7.
7 centimeter. That's the first information you have to pull out from this statement. Then the rest of the part is pretty simple. Once you get the 7, এইটুকুই হচ্ছে মানে কোশ্চেনের চ্যালেঞ্জিং পার্ট, বাকিটুকু সিম্পল। Then it says that the 200 gram mass is replaced with a 100 gram mass. What is the new length of the spring? So for a 100 gram mass, the extension is supposed to be 1. Original length 7. 7 plus 1 centimeter gives you 8 centimeter. So that makes B the correct response. বুঝে গেছে কিনা?
Yes, sir.
বলুন দেখো, বাকি সবাই পড়ে দেখো, যদি কোনো কনফিউশন থাকে আমাকে বলো, আমি এটা কিছু লিখি নাই বিকজ I explained it, but if you have questions, please ask me, I'll help you. All right. We still have some 60 minutes to go by. So let's try at least 1 or 2 problems from the paper 2 maybe. Oh. Let's try number 4. I like this one. Let's see the pages side by side. Should be an easier way to go by. A bit more space. Okay. লাভ হলো কোনো? লাভ তো হলো না। Never mind. Could not achieve what I was going for. Acha. Question of 4 আমরা একটু দেখি। It says figure 4.1 shows apparatus used to obtain the readings for a graph of force against extension for a spring. The masses added to the pan produce a force that stretches the spring. State what is meant by the mass of a body. How do you define the mass of a body? Anyone?
The amount of matter in something.
বিভিন্ন ফর্মুলা দিয়ে ডেরাইভ করে বলা যায় স্যার, বিকজ ম্যাথস একদম বেসিক 7 ইউনিটের মধ্যে একটা।
Yes. So defining mass can be a bit troublesome. It's something like,
What is the meaning of what or why?
yeah. I sometimes mess with my students, asking them the question that, I mean, you all know what the alphabets are look like, but at very primary thing, I mean, if you are asked why an A looks like an A, there is no answer to this question. Someone somewhere defined it to be like that. It has been like that ever since. You cannot logically produce an answer that why an alphabet looks like an alphabet. So, I mean, the reason I'm telling you this is because this is what happens when very fundamental questions are asked, like this one. So, what is meant by the mass of a body? I think it is the answer that the amount of substance present in a body is the mass of the substance. I believe that's the correct response. I'll still have a look. ভুলে যাই সবকিছু। এটা হচ্ছে কম্পাইলেশন কত যেন দেখতেছিলাম। Elasticity হচ্ছে compilation. Oh, 2. Beautiful. আচ্ছা, কাছে থাকবে। Number 4. Amount of matter or material substance you're going to. Oh, yeah, works. Beautiful. Nice. Thank you. এরপর বলছে হচ্ছে describe how the scale is used to find the extension of the spring. So in this case, you have to use a little bit of experimental procedure. The idea is that when load is applied, the marker moves down by subtracting the new reading and the previous reading. We can find the extension. So you have to go a little description, although there is only 1 mark, but you have to write the whole thing. Number B, figure 4.2 shows the force extension graphs for 2 different springs. একটু বড় করতে পারি আমি এটাকে। হ্যাঁ, ঠিক আছে। A student states that spring B is easier to stretch than spring A. Use values from figure 4.2 to explain what the student means. So this is what this is the something that I was about to explain a bit earlier, that if you're trying to explain that which is easier to stretch or difficult to stretch, you either have to choose a single value of extension and compare the forces, or you choose a single value of force and compare the extensions, but keep one fixed and compare the other 2. So if I want to go compare spring A and spring B, there are many different pair of values that you can choose from this graph. For example, if you want to compare them for an extension of 4 centimeter, if you want to, I can go with like that to achieve a 4 centimeter extension on both the springs, spring A requires 20 Newton force, whereas spring B requires only 50 Newton force, proving that spring B is easier to extend. So it requires less force. এটা হচ্ছে একটা উপায়। Or another way you can go by that if you apply the same amount of force on both of them, one will extend less, which means it is harder to extend. The other one will extend more, which means it is easier to extend. So if you choose any value over here, you could choose any value. I would conveniently choose 15 Newton because I can see there is a very beautiful cross point over here and a beautiful cross point over here. This would respond to 3 centimeter of extension. This point will respond to 4 centimeter of extension. So I could choose 50 Newton. This is just a simple way of choosing specific points that makes your explanation more accurate and easier to go by. So I could say that if we apply same 50 Newton force on both the springs, spring A has an extension of 3 centimeter, where spring B has more extension of 4 centimeter, proving that spring B is easier to extend. So you could go by any of the process approaches. Both of them are equally acceptable. You can choose. 2 says when a force of 25 Newton is applied, spring B reaches its limit of proportionality, but spring A does not. Explain how figure 4.2 shows this. So it's about the curvature. So you can say that beyond 25 Newton force, spring A graph is still a straight line, proving that force and extensions are still proportional to each other, which means limit of proportionality has not yet been reached. But beyond, for spring B, beyond 25 Newton, the graph becomes a curve, which means the ratio of force and extension is not a constant anymore, hence proving that limit of proportionality has been overrun. You could write in your own words. I think I said too many sentences for a question number, for a mark of 1. Let's have a look at the mark scheme. How did they articulate this answer? Idea that A is a straight line and B is not, or gradient constant in A but not in B, or same case in F or same. Okay, yeah, any of them, any of these 3 are good. I actually talked about both of them, so yeah, works. B2, let's have a look at the majority of candidates made sensible reference to the shape of the lines in figure 1.2. There was a tendency in some answers to refer to spring B without any reference to spring A, and it would appear from their answers that some candidates confuse the limit of proportionality with elastic limit. Hey, this is one of the key points, that you are not even supposed to bother about the existence of elastic limit. So disregard the presence of that and just stick to the stuff that you are supposed to know. That works better. The same force is applied to each spring. Use figure 4.2 to determine the force that produces an extension of the spring that is 1 centimeter greater than the extension of spring A. এই কোশ্চেনটা ভালো করে পড়ো সবাই, কোশ্চেনটা বুঝে এই কোশ্চেনটা আনসার করার ট্রাই করো। Read. It's a simple question, but language can be deceiving at times or difficult at times. এই নাম্বার 3 কোশ্চেনটা পড়ো সবাই, ভালো করে পড়ে বুঝে আনসার করার ট্রাই করো। Hello, আপু, আসসালামু আলাইকুম।
Sir, 15 Newton.
I'm back. So কোশ্চেনটা বুঝছো সবাই কি বলছে?
Yes, sir. And I think it's 15 Newton.
You are asked to find out the exact value of force that produces 1 centimeter additional extension in spring B compared to spring A. So which one is the correct response? 15 Newton. 15 Newton produces exactly 1 centimeter additional extension in spring B. Can everybody see that from the graph, that you have exactly 1 centimeter additional extension? Everyone?
Yes, sir.
আচ্ছা, তোমরা এই P2 কোশ্চেনগুলো ট্রাই করো। আমরা নেক্সট ক্লাসে ইনশাআল্লাহ এই P2 কোশ্চেনগুলো আলাপ করব, and we might as well start going back to discuss the earlier problems that we left from মানে force acceleration motion chapter. Thank you very much. আজকে ক্লাস এইটুকু পর্যন্ত ক্লোজ করে দিচ্ছি। আল্লাহ হাফেজ। ওয়ালাইকুম আসসালাম।
স্যার
হ্যালো
স্যার, অ্যাকচুয়ালি স্যার আমি তো নতুন স্টুডেন্ট, স্যার আজকে আমার ফার্স্ট ক্লাস, তো আমার অ্যাডমিশন কিভাবে কি করব?
তোমার নাম কি?
স্যার গোলাম মুস্তাকিম।
আচ্ছা গোলাম মুস্তাকিম, তুমি আমাকে মেসেঞ্জারে একটা পার্সোনাল মেসেজ দিও যে স্যার আমি অ্যাডমিশন নিয়ে আলাপ করতে যাচ্ছিলাম, আই উইল রেসপন্ড টু ইউ আফটার দ্য ক্লাস। আমার এখন আবার একটা ক্লাস আছে, সো আমি 9:30 পরে শেষ করে ধরো 10টার দিকে তোমাকে রিপ্লাই করতে পারি মেবি।
ওকে স্যার,
থ্যাংক ইউ, আল্লাহ হাফিজ।
আল্লাহ হাফেজ।